For this video, we have another example of using the first derivative test to decide if we have relative maxes or mins, and we're doing this analytically. So step one is to actually take the first derivative, and I have to use the quotient rule because I have division of two polynomials here. I have a rational function. So h prime of x equals, we're going to have the bottom function, 2x minus 1, times the derivative of the numerator, 2x minus 4, minus the numerator, x squared minus 4x plus 4, times the derivative of the denominator, 2, all over the denominator squared. Now what I'm going to do is actually work to simplify my numerator. I'm going to leave my denominator alone. So when I multiply these two together, I get 4x squared minus 2x minus 8x plus 4, and I'm going to go ahead and distribute a negative 2 into this. So minus 2x squared plus 8x minus 8. I'm going to combine like terms. I have a 4x squared minus 2x squared is just 2x squared. A negative 2x minus 8x plus 8x is just a negative 2x. And then looking at my constants, I have a 4 minus 8, so negative 4. And that is over my denominator squared. So when you're doing the first derivative test, you're taking the first derivative and you're going to set it equal to 0 and check where it's undefined to find critical numbers. So to see where it's undefined, I can look at my numerator right here. And if x equaled 1/2, then this denominator, I'm looking at the denominator would equal 0. So x equals 1/2 would be a critical number if it's actually defined on the original function. Now I'm going to include it in what I do anyway because I know something is going on at 1/2. So I can take my 1/2, go check my original function, and you can see that 1/2 would make my denominator 0 here as well as here. So my function is actually not continuous at 1/2, which explains why it's not differentiable. The derivative doesn't exist there either. So I'm going to keep this. It's not an official critical point because by definition the critical points have to be defined on the original function, but it is definitely something I need to be aware of. We have a discontinuity. To figure out where my derivative is actually 0, I'm going to set my numerator equal to 0. So 2x squared minus 2x minus 4 equals 0, and I'm going to start trying to factor it so I can see that I can pull out a 2. And I have x squared minus x minus 2 equals 0. I try to factor this, and we'll see if this works. We should have two binomials. So factors of 2 are 2 and 1, and I need them to add up to get a negative 1, which I can do. I can make this a minus 2 and this a positive 1, so there should be an x there. Negative 2x and a positive 1x does give you a negative 1x, and a negative 2 times a positive 1 gives you a negative 2. So when I set my factors equal to 0, I have x equals 2 and negative 1. So these are my critical numbers. The x equals 1/2 is just something I need to be aware of, and I am going to use in my number line. So important numbers are negative 1 and 2, and I'm going to put the 1/2 on because my function is not defined there and neither is my derivative. So to check the signs of this, I'm going to be actually plugging into my derivative. Now the factored form of my derivative would be h prime of x equals 2 times x minus 2 times x plus 1 over 2x minus 1 squared. Now I'm plugging in values from these intervals, and I've got 4 intervals, into this derivative to see if my derivative is positive or negative. Now it's important to note this squared. No matter what I plug in here, I'm going to get a positive number because it's squared. Now you might think not everywhere if I plug in a half, but I'm not going to plug in a half. A half would give me 0, and I already know my derivative is undefined there. So basically I get to ignore the denominator. So we're going to ignore that. Because if I divide a negative by a positive, I get a negative. If I divide a positive by a positive, I still get a positive. So this is negligible. So now I'm going to pick a number, and I might pick something like negative 10. Negative 10 minus 2 is a negative. Negative 10 plus 1 is a positive. A negative times a positive is negative. So my original function was decreasing. If I pick a number between negative 1 and 1/2, I might pick 0. 0 minus 2 is a negative. 0 plus 1 is a positive. A negative times a positive is negative. So it keeps decreasing. So basically, I do not have a min or a max at x equals negative 1. If I pick a number in this interval like 1, 1 minus 2 is a negative. 1 plus 1 is a positive. A negative times a positive is negative. So I have an asymptote at 1/2, something decreasing on one side, and it'll be decreasing after. You can imagine it coming in from the asymptote. I pick a number out here, let's say 5. 2 times 5 minus 2 is 3, a positive, and 5 plus 1 is a positive. My derivative is positive there, and these are signs of not f, but h prime of x. So 2 is a critical point, and you can see before 2 my graph was decreasing, after 2 it was increasing, so I have a min. So I could say h of x has a relative min at x equals 2. And I know that because h prime of x changes from negative to positive. Lots of dots there. At x equals 2. And those are 3 different examples when you combine the 2 videos of the first derivative test.